Magnetic fields, part 4. In part 1, we introduced the Biot-Savart Law. In part 2, we used both the Biot-Savart Law and Amperes' Law to derive expressions, useful expressions for the magnetic field around wires and coils and stuff like that. That also led us to a challenge of showing that Amperes' Law and the Biot-Savart Law are the same thing. And I don't think I really succeeded in part 3, but we did get to meet new friends, vector calculus, the div and curl functions. But that got me thinking, can I derive the Biot-Savart Law from Amperes' Law using Maxwell's displacement current? Well, no, I couldn't do that, but this guy could. Robert Buschauer, pardon the mispronunciation, wrote about it in the physics teacher. Look up his article. Here's a run-through of it. Turning this into that begins with expressing Amperes' Law in a new way. Is I really the same as epsilon naught d phi e dt? The electric flux? Not sure I buy that. There is some justification if you consider a parallel plate capacitor and then charge builds up on the plates. Phi is the flux of the electric field, so there is some justification for I equals epsilon d phi e dt, but we'll just have to suspend disbelief and get going. With this shape here, a charge moving towards a ring. No, not just a ring, a surface, kind of like a thimble-shaped surface or a bowl, perhaps, held perpendicular. Well, Amperes' Law tells us that. That's just for the ring. Using Maxwell's displacement current, which is what you call epsilon naught d phi e dt, we'll write this, and that will be the equation that we'll come back to at the end of this presentation. Most of the work will be on this term here, d phi e dt. How does the flux of the electric field through that surface there, how does that flux change as the charged particle moves to the right? Again, phi is the electric field times the area, dot product really. Good thing we know the equation for the electric field around a point particle. But because this is a curved surface, really part of a sphere, we'll use spherical coordinates, which aren't as good. I mean, they're pretty, you get used to them eventually. Trust me, you get used to them, and that's a pretty tough looking equation. Let's take a look at it though. We're trying to find an area. We have two integrals, okay. We have r squared, constant r, okay. We have the integral from 0 to 2 pi d phi, which is 2 pi. So far, so good. We have the integral from 0 to theta of sine theta d theta. That gives you the cosine. Cosine of 0 is 1, of course. Cosine of theta is theta. And if it looks like these two are in the wrong order, it's because the integral of sine is negative cosine, so we flipped the order there. Oh, hey, fun fact. If you integrated from 0 to pi, integrated theta from 0 to pi, phi gets integrated all the way to 2 pi, but theta gets integrated from 0 to pi. If you did that, then hey, the area of this sphere would be 4 pi r squared, just what it should be. Right now, however, we'll be happy with that expression. Again, you notice how you have a complete ring, so that's the 2 pi, and then you're just going from 0 to theta in the other dimension. All right, phi is E dot A. E, A, insert, simplify, differentiate. Nice, we're making excellent progress here. We have d phi dt, but what the devil is d cosine theta dt? How does that angle change? How does, well, not just the angle, but how does cosine theta change in time as that particle moves towards that ring? We'll get some help from the chain rule. D cosine theta dx, dx dt, because dx dt is velocity, and we should know the velocity of this charged particle. Now, what is d cosine theta dx? It's a special result, and we'll pause to solve it, switching to Cartesian coordinates, and we'll dilate on this step right here, d cosine theta dx, the change in cosine theta. How does that work? Well, it's a squared over r cubed, which means that if r is really big, if r is much, much bigger than a, then cosine theta does not change very much as you move towards that ring. But as you get closer to that ring, then cosine theta starts to change more rapidly. Notice, however, that a can never be bigger than r, so don't worry, your change in cosine theta will never be greater than 1. Anyway, let's use this fact about sine theta to finish our proof. Nice. Now, we can have a drastic change in font. I don't know which font I like better. I don't really like either of them. Anyway, let's finish this derivation with one final step. We were looking for this value for d phi dt, and we found it. So we'll use it, and we can rearrange. Dividing by 2 pi, dividing by a. It's good that a cancels out there. I like it. Charge times velocity, that's a current. We can say, we're being hand wavy here with the displacement current, but I'd say that's the Biot-Savart law from Ampere's law.